Hey everyone, welcome back. Have you ever wondered how memory allocation works under the hood in C++? Or why some applications feel snappy and efficient while others are sluggish despite similar logic? Today, we are diving deep into custom allocators in C++, what they are, why they matter, and how they can give you fine-grained control over memory management in your programs. Let's start with the basics. What is an allocator? In simple terms, an allocator is a policy object that handles memory allocation and deallocation for containers like std_vector, std_list, and others. By default, the C++ standard library containers use std_allocator, which allocates memory from the heap using new and delete. But sometimes, we need more control over how memory is allocated. That's where custom allocators come into play. Let's visualize this with a simple example. This works fine, but behind the scenes, every time the vector resizes or reserves memory, it calls the default allocator to get memory from the heap. Now, imagine you are building a real-time system, or a game engine, where performance is critical. You don't want frequent heap allocations, they are slow and can cause fragmentation. Custom allocators let you use memory pools, avoid frequent allocations and deallocations, align memory for SIMD instructions, track allocations for debugging, and improve performance and determinism. In performance-sensitive environments, these benefits can be game-changing. Let's say you want to allocate all memory from a pre-allocated buffer, a memory pool. With a custom allocator, you can do just that. Here is a super simplified custom allocator that allocates from a static array. Here is its usage. This is a very crude example. We are not handling deallocation or alignment here, but it gives you the idea. To make custom allocators compatible with STL containers, it needs to define certain members, like a value type member, the allocate function, the deallocate function, and a copy constructor template. Most of the complexity comes from making it work with STL containers that copy and rebind allocators across types. In C++ 17 and beyond, the allocator model has become simpler, but the general structure remains the same. Let's take a look at a more realistic example that also supports the allocation. You can now use this allocator with standard containers. Why not just always use a custom allocator? That's a good question, but custom allocators add complexity. For general applications, the default std_allocator is fast and optimized. But in real-time systems, embedded programming, financial trading platforms, or high-performance games, where every cycle counts, custom allocators provide predictability and performance. Another reason: debugging. You can write a custom allocator that logs all allocations. Now you can see exactly when and how often allocations happen. Let's talk about real use cases where custom allocators really shine. Memory pools. In a game, you might allocate 1000 entities at the start. Instead of allocating them one by one from the heap, a pool allocator grabs a large chunk once and carves out space as needed. Second, arena allocators. You pre-allocate a big chunk of memory and allocate from it linearly. When done, you reset the whole arena. It's fast and avoids fragmentation. Third, stack allocators. Memory is allocated and freed in a strict LIFO order. Last in, first out, just like a call stack. Perfect for temporary allocations. Fourth and last, shared memory or custom heaps. Allocators can be built to allocate from shared memory or GPU memory, or even custom OS-provided heaps. Important to note, not all STL containers use allocators the same way. For example, std_list allocates each node separately. A pool allocator makes a huge difference here, but std_vector grows its capacity exponentially and uses realloc style behavior. Allocator efficiency may vary. Also, when containers are copied, STL may copy or rebind the allocator depending on the allocator's propagation traits, especially in C++ 11 and later. You can write your own classes to be allocator aware. For example, this way your custom types can benefit from the same allocation strategies as STL containers. Ever had a memory leak or a mysterious crash? Custom allocators can help track number of allocations, size of allocations, leaks, and dangling pointers. By overriding allocate and deallocate, you gain full visibility into what's happening at runtime. C++ gives you the tools to manage memory precisely. The allocator system is part of that toolbox. When you use a custom allocator, you take control of one of the most fundamental parts of your program, the memory. It can lead to more efficient, more predictable, and more robust software, especially in systems where performance or resource constraints are critical. Should you use custom allocators for every project? Absolutely not. But understanding them gives you an edge, and the power to optimize when it really matters. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one.